Welcome to OsmoDevCall number 6 about SS7 and SIGTRAN in 2, 3, and 3G networks. It's mostly, how it is used by 2G and 3G networks, and not so much what they do with SS7, but how they use the underlying SS7 network and how that works and how that is put together. So this talk is about SS7 basics, such as links, link sets, MTP, point codes, routing, ASPs, ASs, and so on. Lots of other acronyms with multiple 2 to 5 digits, I think. We will not be speaking a lot about the applications that use SS7, like TCAP map, CAP, BSS map, and so on in cellular networks. We will also not be talking about, at least not a lot about security topics. So this really is let's say the bottom half of SS7, or I would say the bottom 2/3 of SS7 that will be covered here. Just slightly increase the font size since we have the screen real estate. So if we look at this, oh, that was too large. We have to look at evolution of telephone signaling because that's where SS7 originates from. If we go back like more than 100 years, we end up with manual switching, basically phone checks in large boards that human operators plug in to make connections between telephone lines. Slightly later, then there was automatic switching by inline signaling with mechanical switches based on pulse dialing. So there's the Strauger machines, or in German, the Hebdrehwähler, for example, which were electromechanical devices used for switching between circuit switched analog telephone lines. Later, there was analog switching. Analog switching could be done by transistors, for example. So we have semiconductors in the switching matrix instead of relays and mechanical devices, and but still inline signaling, for example, based on DTMF, the dual tone multi-frequency digits. And these systems were not just used between the subscriber and the telephone exchange, but they were also used over longer distances between the telephone exchanges. Then later on, digital switching was introduced of analog circuits. So the lines were still analog, but some digital switching technology, control technology. And last but not least, digital switching of digital circuits before VoIP came and destroyed everything. If we look at SS7, in terms of the signaling system 7, that's what SS7 stands for, sometimes also called C7 for CCITT, signaling system number 7. So C7 and SS7 are terms used interchangeable. So the first real international digital switching system widely deployed that I'm aware of is in 1964 was C5, the signaling system number 5. It uses tones inside the voice circuits, so it's similar to DTMF basically, and it can also be used in digital circuits where then the tones are played as PCM samples. In 1972, signaling system number 6 was introduced, which was the first system to use digital messaging to relay signaling information between telephone exchanges. It predates the protocol layering of the OSI ISO model, and it has a monolithic structure. So there's no separation between, let's say, transport layer and application layer and network layer and so on. And it was intended as an international system to be used, but it was never really widely deployed outside of the US because basically SS7 happened, and that was then deployed worldwide. Originally developed by AT&T in 1975 and first published in 1980 by CCITT. I'm not going to pronounce it. It's a French acronym. I will only do that wrong. Maybe Kevin can help with that in case anyone is interested. So it's now the ITUT, the technical part of the International Telecommunication Union. And it was released as the so-called Yellow Book. And every 4 years, all the standards have been revised and published as another book with another color. So there was Red Book in 1984 and Blue Book in 1988. And then from 92 and onwards, all the specs have been separated in separate specification documents. So it's not just one book released every 4 years, but every individual spec is released whenever they feel like there's a new release to be made for this specific document. So all of this is called SS7. And there's some interesting statistics that show you that basically in 20 years, the spec number of pages in those specs grew by a factor of 18. And all of that is still SS7. So it's it can mean quite some different things. So if we look at the traditional use case, as I said, telephone switching, so it's signaling between circuit switch telephone exchanges. And that signaling happens adjacent to the circuit switch telephone lines. So it was never something that is used towards the end user. So a subscriber or an end user doesn't speak SS7. It's the telephone operator internally or multiple telephone operators among each other that exchange signaling information by SS7. So in the diagram you see at the bottom, you have subscribers at the left and the right end. In this case, these are ISDN subscribers. They use Q931, also known in Europe as Euro ISDN, as a signaling protocol towards the telephone exchange or telephone switch. And the telephone switch then connects to other telephone switches over SS7 and uses the ISUP application level or user level protocol to convey signaling to other telephone exchanges. And finally, at the remote end, the telephone switch Y in this diagram then again converts to ISDN Q931 signaling towards the subscriber. So it was never set on these subscriber interfaces, but between telephone exchanges and for circuit switch telephony. So we have to put this in context. This is at a time where IP maybe existed on paper, but not widely deployed. And also the classic telecom operators, the circuit switch world, never really thought that, I mean, they had their own world and their own systems and everything was circuit switched and there's no IP or packet-based interface between those elements. In terms of the protocol layering, as I mentioned briefly already, SS7 was the first signaling system to employ protocol layering based on the OSI ISO model. And we have mainly the MTP, the message transfer part, as the lower level or lower part, which is further subdivided. We will look into that. And then some initial user parts on top of that. The user parts are identified by the EUP at the end. So we have TUP, the telephony user part. We have ISUP, the ISDN user part. And those user parts then are, let's say, application-specific protocols that use the means of the underlying message transfer part to get messages relayed between telephone exchanges. Later, there were some other protocols added, like SCCP and TCAP. We will get to that slightly later. So in terms of the nodes and addresses in those networks, all of the nodes in an SS7 network are so-called signaling points. So an SP, any element that somehow speaks SS7 is a signaling point. And each such node or signaling point has at least one so-called point code, which is the address inside the SS7 network. Interestingly, these addresses have a different length depending on the country or region you're in. So internationally, between countries at the international interworking interfaces between operators, there's a 14-bit ITU, so-called 14-bit ITU-T point codes, whereas North America and China have decided to use 24-bit point codes, and Japan decided 16-bit is an interesting compromise in between. I'm not sure how that came about. But in any case, that is how it is. So basically, you have the same signaling system, but different lengths of addresses depending on where exactly it is spoken. which also means that there's a need for translation in between those gateways between those different network domains. Which brings us to sort of the type or the network indicator inside associated with point codes. The point codes can either be international, or they can be national, or they can be reserved. There's actually 2 reserved types. And this is a bit to separate those different addresses. If you think of IP networks, then we have one space of IP well, IPv4 in that case, one space of IPv4 addresses, and basically some parts of that, like the 192.168.0.0/16, have been designated for private networks. In SS7, it's different. Sort of the indication what type of point code this is separate and is next to the address. So you have the full, let's say, we talk about international format, ITU format, 14-bit. So you have a full 14 bits for international point code and another 14 bits for national point codes in every nation. And then you have additional 14-bit addresses for internal or private networks. And they are not basically inline divided like IP addresses, but there's an external property that indicates what type of point code a point code is, whether it's international or national. And there's no direct routing between those different point codes. So if you have point codes within, let's say, a national German network, then you can route to other nodes within Germany, but internationally, there's a, let's say, it's a different address space of point codes. So there's no direct, they are not globally unique. Only the international ones are globally unique. Yeah, so we have different types of signaling points in the network. As I said, a signaling point is every node inside the SS7 network. We have 3 different types. One is the STP, the signal transfer point, which is responsible for transferring SS7 messages, yeah, too many typos, between SS7 nodes. And you can compare this to a router in an IP network. So if you look at the diagram here, we have 2 STPs in here, and we have SSPs, and SSPs are the service switching points, which are telephony switches or telephone exchanges, which originate or terminate SS7 messages, but they don't route them. So this is like a host with a single network interface, and this is a router with multiple network interfaces if you want to look at it from an IP point of view. So SSPA wants to talk to SSPD, then it sends a message to its STP, and this STP routes it to another STP, and that STP routes it to the destination, the SSPD in this diagram. There's also service control points, which are interfaces between telecom databases and the SS7 network. The distinction between SCCP and SSP is mostly esoteric from my point of view, so you can just look at them as identical. I mean, STPs are routers and everything else is end nodes. It's sort of a logical conclusion from that. Now, we see here the connections, of course, between SSPs and STPs and between STPs and STPs. How do they look like? So we've spoken about the nodes. How do the edges look like in this network? We have so-called links and link sets. Or rather signaling links and signaling link sets, but I guess it's all about signaling, so we can ignore that part. Links are point-to-point connections between 2 signaling points. And that's important to realize that there is no notion such as a broadcast medium with multiple entities attached. There is not the equivalent of an Ethernet link or something like that. It's a point-to-point interface where there's one sender and one receiver, and of course the reverse direction, so bidirectional, but it's point-to-point interface, such a link between 2 network elements. Classic SS7 links are 64 kilobit time slots in PDH or SDH network, the classic TDM networks. Later also there was specification added for high-speed signaling links, HSLs, which use a full T1 or E1 that's like 1.5 or 2 megabits as a single link, but those are relatively rare. So it's 64 kilobit classic links. Then you can aggregate multiple of those links into so-called link sets. And the reason for that is that you get redundancy between those links, and also bandwidth aggregation, if they're all up, of course, within a link set. And links of a link set are between two signaling points. So they must have the same two endpoints. And in this diagram, we see a signaling link set between signaling point A and B, consisting of 3 links in that link set. Then there's all kinds of link types, which I will not go into detail. That ends up with complex diagrams, but this is basically just a, let's say, how a link set is used determines its designation. So there are A links, B links, D links, E links, F links, and so on. We can ignore that for the course of this presentation. In terms of routing in this network, it actually works surprisingly similar to IP. We have a point code and net mask. I think it's only called mask here in SS7. In a 14-bit point code network, of course, a /14 then is like a /32 in IP. So it's a single host or single signaling point route, and the default route would be 0/0 in the routes. One key aspect is that routes are typically statically provisioned at each signaling point. So this is there's no BGP or no OSPF or anything like that in SS7, at least not traditionally and then not typically, even though there are, of course, mechanisms how to indicate that a certain point code is reachable or has become unreachable. There's no real like dynamic routing or something like that. So if we look at the different protocol stack layers, from top to bottom in inverse order, we have MTP1, which is the physical layer, our 64 kilobit TDM circuit or time slot on an E1 line, for example. On top of that, we have MTP level 2, which is a data link layer that takes care of encapsulating messages into variable length packets. So we have link alignment, link error monitoring, error correction, flow control, and these kind of tasks on MTP2. And then on top of that, we have MTP level 3, which is the network layer of the network. And it consists of 2 different parts, the so-called SMH, the signal message handling, which is the forwarding and routing of messages based on point codes. And we have the SNM, the network management, which monitors link sets and routes and provides status to nodes. So if some point code becomes unreachable, it notifies the peers that this point code has become unreachable. There's a question about no dynamic routing at all. Well, I mean, the specs don't forbid you from doing whatever kind of intelligent logic on top within your network, but between operators, I'm not aware that there is you have redundant links, and you achieve redundancy by having all kinds of redundant connections, so multiple link sets in each link and multiple links between each pair of STPs and multiple pairs of STPs. So redundancy on redundancy on redundancy, but there's not a way how you can advertise across an entire network that a new address has been available like you can do in BGP or something like that, at least not on a global scale between operators, as far as I'm aware. So yeah, we have these 2 parts, these 2 jobs of MTP3. Now, an MTP3 header, actually, I forgot to include it here now that I realize it. It consists of an origin point code, an OPC, and a destination point code, a DPC, the network indicator, and some other bits here and there. But mainly it's the, like in an IP header, you have a source and destination address. Here it's an origin and a destination address. And it's a 14-bit point code in those messages. And when the messages are received here, it's like IP routing. So STPX receives a message for a certain destination point code. It consults its routing table, it reaches a routing decision, and then it decides to which other STP or SSP to route the message based on the routing table. So nothing different there. Yeah, so the first user parts on top of MTP that were deployed in 1980 is the TUP, the telephony user part, and then later the ISUP, the ISDN user part, which are signaling protocols for signaling of analog telephony or ISDN telephony calls. I think TUP, I'm not an expert, I don't work at operators, and maybe there are some countries that still use it. ISUP you still see quite a bit in terms of signaling, also related to cellular networks, but TUP, I'm not aware how wide you would still find it today. Both of those work directly on top of MTP3, which means the only addresses that there are to route those messages are the point codes, and so every switch needs to have its unique point code, and you can route the messages to those different point codes. We'll not look into those in detail now, because we want to look at some of the other protocols that are more relevant to cellular networks. There is, for example, the SCCP, the signaling connection control part, which operates on top of MTP3. So you have MTP1, MTP2, MTP3, and then SCCP on top. And as you will notice, it is not a UP, not a user part like TUP or ISUP, but it's an intermediate layer that represents the OSI model layer 3, the network layer. It provides the transport of so-called non-circuit related signaling. So it transports information that is not about a circuit switched telephone call, even though it uses the same signaling network. There's split between two functionalities, the so-called connectionless transfer and the connection-oriented transfer. Connectionless, you can compare a bit to UDP. You have datagrams that are sent from source to destination. There may be response datagrams, but no abstraction of a connection. Connection-oriented transfer, you cannot really compare with TCP because it is not a stream. It's individual messages, datagrams, but with the notion of a connection that is established, and then you have messages both ways, and it is torn down at some later point. It adds an additional layer, SCCP adds an additional layer of highly flexible addressing on top of MTP, where MTP only has point codes. SCCP has SCCP addresses, which we will look at shortly, what those are. SCCP now with, of course, the underlying transport protocols were and are extensively used in cellular networks of 2G and 3G technology. Not only on the most people associated with the roaming interface between operators, but it's also used on the A interface, which is the interface between the radio access network, base station controller, and the core network. And likewise in 3G, it is used for IOCs and IOPs between the radio access network, here the RNC, and the core network. And it's used for virtually all interfaces in the core network itself, so between the HLR, home location register, and the SGSN, and another SGSN, and the SMSC. I wanted to put SMSC there. You see too many acronyms. So the SMS service center and the home location register and the mobile switching centers, they, for example, all use SCCP to communicate their high-level protocol messaging. So SCCP addresses, they can be, and that's quite strange. I've never seen anything like that in any other protocol. Normally, you have a protocol, and the protocol has one type of address. You know, Ethernet has MAC addresses, and IP has IP addresses. But SCCP, you have addresses that can be, well, it could be just a point code, or it could be just a subsystem number. A subsystem number, you can think of, let's say, a TCP or UDP port number. The SSN indicates what is the next higher level protocol, or what is the user on top of SCCP. So you demultiplex based on that. Or it can be global titles. And global titles now you can think of as telephone numbers, but on steroids somehow, different types of telephone numbers, or things that look like telephone numbers but are not telephone numbers. Let's say sequences of BCD digits, could also be IMSIs, for example, and not just telephone numbers in there. So you can have an SCCP address that contains either 1 or 2 or 3 of those above. And then in addition to that, the address specifies whether routing should be performed on point code and or subsystem number if they exist, or if routing should be done based on the global title in the message. And that now offers a lot of flexibility in many ways in which things can go wrong. It can be confusing at times. Now, one additional oddity in SCCP is if you look at connection-oriented SCCP, unlike IP networks, the calling party address is only visible in the connection setup. So think of something like TCP, where you only see the port numbers in the SYN packets, and then in all the SYN-SYNAC in the setup handshake, and then later on there is some other number that is dynamically allocated that is used to identify the source and destination. And to make things worse, the individual datagrams within a connection you only see the destination local reference, so basically where it goes to. You don't even see where it comes from. So a lot of information is not present in the messages, which is generally something you see a lot in circuit switched networks or circuit switch technologies. Unlike in packet switch technologies, where typically you have all the address information in each packet, the source and the destination, so you always know where it's coming from and where it goes to. Built-in privacy if you miss the call setup during interception. Yeah, I think the only reason why they did this that way is that SCCP addresses can be relatively large. I mean, if you think of, let's say, a fully qualified international telephone number, one for source and one for destination, plus some additional bits, so the addresses get relatively large. And this is all spoken over 64 kilobit links. So I think it's mostly you want to squeeze and remove every byte that you don't need to transfer, you don't transfer, to ensure you don't overload your signaling links. Which basically brings us to another interesting topic, which is the topic of the maximum size of signaling messages, where there is not really any mandated minimum size that I'm aware of. Well, maybe there is one, but in any case, in practice, you never know how large you can make messages so they reach the final destination. So there is no path MTU discovery or anything like that. So if you want to make sure that your message can be routed all over the SS7 network, you really have to make it very small. And allegedly, this was also the reason why SMSs are limited to 163 7-bit characters, because that was the maximum with the 7-bit packed characters they could transfer over SS7 networks without running into some nodes that would basically discard the message because you hit the maximum supported message size there. Another protocol within SS7 is again on top of SCCP now. So we have MTP1, MTP2, MTP3, SCCP, and now on top TCAP, the transaction capabilities application part, which is also a really odd thing to get your head around because it's not a protocol in itself, like you would know it or like you would recognize it, but it's some kind of concept to generalize out some of the transaction logic from higher level protocols. So TCAP is like an adapter that sits between SCCP and a higher level protocol that takes care of some transaction logic. And its main two users in cellular telephone networks are the MAP, the mobile application part, which is the signaling used between most of the core network elements, and CAP, the camel application part, which is used for prepaid roaming and billing purposes in 2G and 3G networks. TCAP is in itself quite strange. You have a dialogue portion and component portions, and it's been probably 10 years since I started to look into this, and I still find it odd today if I look at TCAP conceptually. Guess if you haven't been growing up with it, you will always find it weird. Okay, so far for circuit switched SS7 basics, how they work traditionally over time division multiplex interfaces. Now, of course, at some point, IP networks became more relevant than circuit switched time division multiplex networks. And one had to think about how to transport SS7 signaling over IP. Why did one have to think about that? Well, if, of course, ISDN or analog telephone lines go away, then you don't need the signaling for ISDN or analog telephone lines anymore. But of course, for an extended period of time that is still not fully concluded, you still have circuit switched lines somewhere on the planet, and you need technologies that can deal with both. So let's say individual parts of the circuit switched TDM network are then carried over IP while others still remain, and vice versa. And also we have all of the cellular network related signaling that doesn't really necessarily relate to circuit switched telephony. Let's say you register to a cellular network, or you send an SMS that is not related to circuit switched voice telephony, but still it uses all this infrastructure. So somehow the SS7 had to be how can I say, adapted or translated on top of IP. And that is what happened in the IETF SIGTRAN working group, the signaling transport working group, which is now long concluded, closed. And it developed a series of protocols, I think in the late 90s, that are designed to help use SS7 over IP. The common denominator to all of those protocols is SCTP, the Stream Control Transfer Protocol, which is a layer 4 protocol that is on the same level as TCP or UDP, directly on top of IP. And then on top, you have various different dialects or versions of SIGTRAN. They're listed all here. I'm not going to read the slide. You can also see on this slide that there's how those different protocol stacks look like. So in a classic SS7 world, if we look at, let's say, a map interface like it's used in GSM or 3G, oh, there's actually TCAP missing. My apologies. I just realized. Okay, so replace the top line with TCAP/map, so it becomes correct. So we have TCAP and map at the top part, which is our, let's say, application layer. And then on the bottom, we have SCCP on top of MTP3, on top of MTP2, on top of MTP1, which is an E1 or T1 time division multiplex line. Vadim is asking what V5 is. V5 refers to ITU-T v.5, which is a protocol used to control remote access multiplexers. Sometimes, let's say, you have a telephone switch in some town, and there is like a remote village which is a bit out of the town, and you want to connect that, but somehow either you don't have the number of lines to connect all of those subscribers directly there, or the line length is too long. Then you put an so-called access multiplexer in that village, where all of the people in that village connect their telephone lines to, and then you have some kind of multiplex connection, like an E1, for example, between this access multiplexer and the telephone switch, and the protocol used to remote control that access multiplexer is V5. And there's V5.1 and V5.2. And I've been trying for years to get hands on such equipment, to play with it and to implement V5 in open source software, but unfortunately I still haven't yet managed to obtain such equipment, but I'd love to. Okay, now getting back to that, so we have the application on top. Here it's map with TCAP built in this diagram, then SCV and so on top, and that's the circuit switched. And now we have all these new versions over IP that all differ in at which level we adapt, like how many layers do we take from the classic SS7 protocol stack and how many layers do we bring in from the bottom. So SUA, the SCCP user adaptation layer, basically takes the minimum IP transport for SIGTRAN, which is SCTP over IP over Ethernet or whatever you have underneath your IP, introduces this SCCP user adaptation layer, and then directly in there you have the SCCP user, right? Map is the SCCP user. SCCP is the MTP3 user. MTP3 is the MTP2 user, and so on in this context. So SCCP user adaptation takes whatever is above SCCP and puts that and glues that on top of IP. With M3UA, we take the MTP3 user, which is SCCP, and we transplant that over here. We add our MTP3 user adaptation layer over SCTP over IP and so on. With M2UA, you go another layer lower, so we have MTP2, and the user of MTP2 is MTP3, so we take everything from MTP3 and upwards over here. We add M2UA, and again we have the SCTP IP Ethernet underneath. And last but not least, there's the MTP2 peer-to-peer adaptation, where you only remove the E1T1, and everything, including MTP2, MTP3, and so on, and all upper layer protocols are still existing in IP. That's what M2PA looks like. So the important thing to take from this slide is that SIGTRAN is not really one protocol, but it's a number of different protocols, all designed within one working group, which was called SIGTRAN. And some equipment now implements M3UA, but not M2UA, or this or that, or whatever. So for example, I think in Cisco ITP, you have SUA, M3UA, and M2PA, but no M2UA. And in some other, so you have to find whatever is the common denominator between the equipment to interconnect. Now, why did they develop all these different versions or variants? Of course, they have all their use cases. And it depends on what you want to achieve. Let's say you have an existing SS7 network, going back to this here, for example, this diagram. We have this existing network. It used to be connected all by TDM lines, and now for whatever reason we want to remove this TDM line, and we want to replace this connection here between those two STPs with an IP-based transport. But we want to keep the STPs like they are, and we want to keep everything else the same. Then in this case, of course, we have to use M2PA as a translation layer, because that's the only thing that is transparent enough for those two STPs to operate without any modifications. So you can basically put a gateway in between, and all the higher layer protocols will not notice any changes. If you want to connect some IP-based service to an existing SS7 network, then of course you will use one of those two, the M3UA or SUA adaptation. And since, for example, with SUA, yes, you can use it with a map-based application. But if you wanted a TUP or ISUP adaptation, TUP or ISUP runs on top of MTP3. It doesn't have SCCP. So where there is no SCCP, there is no SCCP user. So it means you cannot use SUA to translate those protocols. So they all have their explanation. It's not just some random, they couldn't agree on a spec, so they specified 5 different ones, but it is indeed all makes sense. So now let's look a bit at some of those individual protocol layers in SIGTRAN and some of the concepts. SCTP itself is a layer 4 IP protocol at the same level of UDP or TCP or ICMP for that matter. It has source and destination port numbers like UDP or TCP. It is datagram oriented like UDP, but you have reliable delivery, which makes it very interesting. That is sort of like TCP, but then TCP is a stream that doesn't preserve message boundaries, so it is not like TCP. So it's really UDP with reliable delivery. It has built-in support with multi-homing. Multi-homing means you have multiple IP addresses on either side of your SCTP. And that's why they call this association. So in SCTP, you don't talk about a connection. Like TCP has a connection, but SCTP doesn't have a connection. It has an association because it is between any number of IPs on the left side of the association and any number of IPs on the right-hand side of the association. All of those IPs have to belong to the same host on both sides, of course, but you can have any number of IP networks with any number of different addresses in between. And if those some of those IP networks fail, it will transparently continue to work over those that remain. So that's a bit of the link set idea in SS7 translated to IP networks. It also has two parts that make it different from, let's say, TCP or UDP. In TCP or UDP, basically the only knowledge of what higher level protocol you're using, let's say HTTP or SMTP, is the port number. So there's a convention that HTTP is spoken over port 80 or HTTPS is spoken over port 443. In SCTP, in addition to the port numbers, there's a so-called payload protocol identifier field in each message, which tells you what is the payload protocol. So you can use any port number and still you will know based on the PPID what actually is the next level protocol. I find that a very smart decision, and it helps basically for tools like Wireshark. They just look at the PPID and can decode it no matter what non-standard port number anyone might have configured anywhere. It's extremely convenient. It also has multiple parallel streams of datagrams in each association. And each of those have, within one stream, you have no reordering and in-sequence delivery, but those streams in parallel, they can basically be asynchronous to each other. Not quite sure why or what is the real use case for that, but it's one of the significant differences. And actually, the higher level protocols like M3UA make use of that. So some messages have to be sent over stream 0, but some other messages must not be sent over stream 0. So M3UA now operates on top of SCTP, and it allows the MTP3 user to utilize a remote MTP3 stack. So it is not really extending an SS7 network over IP, but it is allowing an external application to utilize an SS7 network, or utilize the MTP3 stack on a remote SS7 node. So you have something called a signaling gateway, an SG, that attaches both to IP and the SS7 network. And then you can have any number of applications in the IP side that can remotely use the MTP3 and underlying stack of the signaling gateway. You can think of it like of a SOCKS proxy in the IP world, where using SOCKS, you can use a remote TCP stack of some gateway. And it's sort of the same idea. M3UA is the predominant SIGTRAN dialect that is used within 3GPP specifications. So the A over IP interface in 2G or the IU interface over IP are both, for example, specified over M3UA. You could, of course, speak them over other dialects, but as 3GPP states, you must support M3UA in order to interoperate with different vendors. Now, all of those SIGTRAN XUAs, if we look again at that, we have M2UA, M3UA, SUA, V2UA, IUA, all those UAs, but not the PA, by the way. All those UAs, we abbreviate them with XUA, so some user adaptation. They have the concept of application servers and application server processes. Now, an application server is a remote SS7 user application. So, for example, you implement a home location register that is the subscriber database for 2G, 3G networks. And you want to connect that to a signaling gateway, then this HLR is an application server. And it connects to this signaling gateway to connect with SS7. An application server is associated with what's called a routing key. Now, a routing key is, for example, a point code and or subsystem number. So in the signaling gateway, you configure point code 23 with subsystem number 8, for example, gets routed to application server X. So any message that SS7 message that arrives at the signaling gateway, which matches this routing key, are then translated and passed to this external application server in the IP domain. What you can specify as a routing key depends on which X in XUA you're using. So in MTP3, of course, you can only use point codes and subsystem. No, not even subsystem numbers. Actually, you can. No, you can only use point codes basically as routing keys. But in SUA, you could also use subsystem numbers, SCCP level subsystem numbers, for example, as routing keys. Application servers have states. Well, down and active are sort of self-explanatory. Inactive means, let's say, the two elements are talking to each other, but they have decided that they are not, this connection or this association is not active yet. And within, or next to application servers, we have so-called application server processes, ASPs. Now, each ASP is an individual connection between a signaling gateway and a user application. It becomes interesting in that it's not that one AS has multiple ASPs, it's the other way around. Every ASP can serve multiple ASs. So you have one connection and it can serve multiple applications over that one connection. And then you can have multiple of those connections, meaning multiple ASPs serving one or multiple application servers in order to achieve redundancies. It's quite interesting complexity that they have hidden in there. In the end, you normally, at least in those use cases that I have seen, you only have one AS served by an ASP. And we will see the relation between those two in the next slide, where we talk about traffic modes. So the traffic mode of an application server determines the message handling in the SS7 to application direction. In the override traffic mode, you have one ASP that is active and all the other ASPs are in standby. So basically, it's just a hot standby kind of scenario where you have multiple ASPs, meaning multiple connections for your one application, and one of them always is active. And if the active one goes inactive or down, then another one becomes active. Or likewise, if one of the inactive ones decides to become active, all the others go inactive. Load share is then a distribution of messages across all the active ASPs within one application server. Of course, for load sharing, as the name implies. And there is a broadcast as well, which is to send copies of each message to every active ASP. So basically, every incoming SS7 message is duplicated any number of times, and a copy of this is sent to each of the ASPs within an AS. Not sure where the broadcast really is used other than some kind of debugging, let's say a mirror port in a switch sort of at a different level. But of course, load share and override are heavily utilized traffic modes. Now, if you want to play with any of that, there is two software packages that I personally find rather useful. One is OsmoSTP. It's the Osmocom implementation of a signaling transfer point. However, it only supports SIGTRAN. It doesn't support classic TDM-based SS7. It comes also with a client library, libosmo SIGTRAN, which allows you to implement applications that then register as clients or as ASPs towards a signaling gateway like OsmoSTP. And OsmoSTP does the MTP level routing and all of that. The other one is Yate, which some people may know as a like PBX or soft switch software in line maybe with use cases that people would normally or more frequently do with asterisk or free switch. Yate has a very strong SS7 stack, including a TDM SS7 stack. So it really does all the MTP2, MTP3 over real TDM interfaces with, for example, DADI cards. It supports M2UA, M3UA gateway, and SCCP with global title translation. So in addition to that, what you can also do, but you're most likely not allowed to do unless you have licenses from Cisco for that. There is Cisco ITP is how the product is called, the Internet Transfer Point. It's basically a combined STP plus signaling gateway that you can run either on like real Cisco hardware, which today, for example, the 2700 series of Cisco devices you can get for like 60 or 50 euros on eBay. If you have a license, then you can install the ITP iOS image on that and also play with the non-open source implementation that has been widely used in production networks. You can also run that in, oh my God, I forgot the name. There's a software emulation of this MIPS-based Cisco equipment. I forgot the name. Maybe somebody can write it in the chat. It's been too long since I last used it, but the Cisco ITP images can also run in that Dynamips exactly in this emulator. That's also a way to use to play with STPs in a virtualized environment without having to buy bulky, large hardware. Yeah, and with that, we come to the end of file. That was my tour through SS7, the lower layers as it is used in the 2G and 3G networks. Do we have questions? The questions now are still on the record part of the recording. In a few minutes, I will switch it off, and then we can also still have question discussions which are not on the recording.
I have a question about the, what was it, the SCCP connection functionality, the transaction functionality. So
connection-oriented SCCP.
Yes. Does the whole SP chain does to know about this transaction? Because you have a relationship between the origin values and then the 24-bit. What was it? There was the other slide.
You mean the 24-bit local and local reference?
Yes.
Where is it? Local remote reference.
So if you imagine you have a chain of like 10 machines, 10 signaling parts. So everybody has to. So the packet has to go to the same 10 machines every time, right?
Yeah. So connection-oriented SCCP, at least the only use cases that I am aware, and of course I mostly know several networks, is only between the RAN and the core network of mobile operators. So you will not have a very complex hierarchy in between. So between the BSC and the MSC, for example, it's not used in the core network or between operators. But yes, you are correct that on SCCP level, normally you only have the source and the destination, and all the intermediate routing is done by MTP. If you have intermediate SCCP level translation or routing, then you do something that's called connection coupling, which is basically a proxy in between. At least that's what the spec states. We've not implemented that. There was never any need for it. But then basically you would have multiple, like wherever you can route you at MTP level, you have a connection, an SCCP connection, where the point codes are sufficient to route those messages in between. And whenever you basically get outside of that domain where you can route, you have this connection coupling in an STP and then another SCCP connection at the other side. And as I said, the connection oriented is really quite special and not really used. For example, TCAP runs on the connection-less SCCP. So all of the map cap and so on, you never have the connection-oriented SCCP in there. Okay, thanks again, everyone, for your attention.